Hello and welcome to C++ 101 Week 6. Today we're going to be talking about pointers. So let's go ahead and get some code running. Now the way I'm going to structure this is we're first going to be talking about pointers, the syntax of pointers and what they do, and then we're going to be talking about dynamic memory allocation, which pointers facilitate. So I'm going to start off with a very simple program, and I'm going to ask people what they think the output of the program is going to be. Alrighty. So given that I have provided values for both the product name and the product price, what do people think that the output of this program is going to be? In fact, I'm going to go ahead, just to make this example more clear, I'm going to add a pause before, after getting the user input, but before we actually display the values of the product. So if I were to run this code and wait a year for it to compile, and give it a product 1 and a product price of 10.10, now if I were to hit enter and enter line 33, what should the output be? Any guesses? Okay, when I hit enter, look at this.
Cool.
What we're seeing here is a string that has indeed been constructed. So the string itself is constructed and set to a default of blank, and we get this. Decimals are not constructed, and therefore the value we get is going to be whatever memory that happened to align with this particular object that I defined on line 30.
A very large negative number, as it turns out.
Yes. So why is this? Let me go ahead and fire up Photoshop really quickly, or find it if it's already open. Are you open, Photoshop? Photoshop is not open, so let's open it. So let's talk really quickly about why this happens. Because why we're getting this behavior is going to be a very, very important aspect to understanding pointers. And for those of you wondering, I am not yet using pointers. There's no pointer being represented here within my code. So don't get confused that if you think I'm trying to show you guys something new, which as of right now I'm not.
No, that's an important point.
Okay. So what's happening? Well, what we get here is a really straightforward bit of logic. We have the call stack, or the stack. Now, within our code, you'll notice that main initializes product P1 on the stack. So main stack frame, when it's invoked by the operating system, contains a product. And a product contains a string and a double. This is main's stack frame, which means the size of main stack frame is at least going to be the size of product. So if we assume that product is, let's say, 32 bytes, we can assume that the main stack frame is at least, that's important, it's not exactly, but it is at least 32 bytes wide. Is everybody good so far? Does everybody understand this? We've been talking about stack frames a lot, and this code inside of main will initialize the product onto the stack frame of main.
And you're saying that the product is 32
bytes long.
So, and that includes the string and the doubles.
Yeah, I don't know the exact number. That's why I defined product as 32 bytes up there.
But I was just checking that it was that 32 was inclusive of the string and the double and any other cruft that's necessary.
So let's say we have another function called getInput that takes in a product. And then we invoke that method within main. We say getInput P1. When we do this, we are initializing a new stack frame. And I'm going to call it getInput. GetInput has one thing on the stack at the moment. Let's assume that getInput for right now just assigns p.name to hey, and it assigns p.price to 10.5. This data right here is added to the stack frame when getInput is invoked, meaning that the getInput stack frame looks like this. The values of P1 get copied into the memory that is allocated when the getInput stack frame is pushed onto the stack. Meaning that when we say p.name, we're actually editing this string. And when we say p.price, we're actually editing this double. Meaning once getInput returns, that will completely destroy this stack frame. And you'll notice that main remains untouched.
Like Kaiser Soze.
I don't know what that means.
And it was gone.
Because the stack frame gets destroyed when the function returns, the data is no longer going to be represented in the main stack frame. It's local to the function. This data that we're getting from a parameter will always be local to the function. Always. Even when using pointers, the data is still a pointer that does get pushed onto the function.
And Florin asked, so when you call getInput from main, you'll push getInput on the stack until it's returned, yes?
Yes. Until the getInput method, the getInput function returns, this remains on the stack. When it does return, this gets erased from the stack, and that data is considered to be unallocated. So how's everybody feeling?
And if you've been paying close attention to earlier lessons, this is basically a review so far.
Yeah.
But with the perspective of a few more weeks. you know, literally you've been coding for probably 500% of the time that you were last time we went through this. So hopefully it makes a bit more sense this time.
Okay. So let's edit this code so that we can use this function as it was intended. What I'm going to do here is I'm going to add two symbols to my file. The first symbol I'm going to add is a star.
No, it's not. It's an asterisk.
Asterisk to our type. By adding a star to the type, we have defined this parameter as a pointer to product. It's not a product, it's a pointer to a product. You'll notice that we get a few more errors though. We get an error on line 15 and we get an error on line 18. I'll explain this in a little bit more detail once we get to the whiteboard again. But I'm going to change both of these member access operators to an operator that is designed for use with pointers. So you'll notice I had to change those dots to these arrows.
Can I make a suggestion? If you renamed your local variable on line 12 to product pointer, it might make the discussion clearer as we go forward. I'm just thinking back to Monday's pointer called pointer of the pointers.
Okay. You'll notice we still get an error on line 31. We get an error on line 31 because get product data from user no longer accepts a product. It only accepts a product pointer. Well, there exists a symbol in both C and C++ that allows us to convert any type or any object into its corresponding pointer object. And that symbol is the ampersand. By doing this, we have successfully converted for P1 from a product to a product pointer, which makes this expression able to be used as an argument into the get product data from user function.
And actually this suddenly, I had a flash of understanding on this on Monday when you suddenly read out someone's question that had that syntax in it out loud because of the way you read that what is highlighted.
Yeah, it's saying
read that out loud.
Get product data from user, passing in the address of P1.
If you read an ampersand in this situation preceding in any situation preceding an object, you can read it as address of.
Yep. So now when I run this code, we'll get the output that we expected. You'll notice we now display the same thing we entered between lines 12 and 20.
Because now, rather than handing in a copy of the product, you're actually handing in basically like a map telling get product data from user where to find the product. As opposed to saying, here's the product, you're saying, oh, it's over there, go and get it.
So, bringing back to the whiteboard, we have an important distinction of what's happening. Let me go ahead and make this guy bigger. That didn't intend what I wanted it to do.
That's because you're an image size, not canvas size?
Correct. Okay, so now I lost my code. Okay. Now what we have is we still have a main. We still have a get input. Main still has a product. Which means when main is pushed onto the stack looks like this. This is the call. This is the stack for main. However, getInput no longer accepts a product. It accepts a product pointer. And the actual code inside of it, to mimic what I had in my previous example, would look like this.
And it's worth noting that arrow is a minus sign followed by a greater than symbol, not an equals followed by a greater than symbol.
Yeah. So now when we invoke getProduct, getInput, something special happens. That does not look like an ampersand.
That's because your 3 was forwards.
Oh. When the stack frame for getInput happens, remember, this product is 32 bytes. When getInput gets invoked, however, what we have on its stack frame is not a product. We have a product pointer. A product pointer on a 32-bit operating system, or a product pointer that has been compiled against a 32-bit architecture, it's going to be 4 bytes.
Mileage may vary.
I'm going to use 4 bytes continuously for now. However, the size of a pointer is determined by quite a few different variables. But I'm going to refer to the size of a pointer as 4 bytes.
The key point being it's a small number of bytes and it will always be the same number of bytes.
Yep.
But it might be 4, it might be 8, depends on your, it might be something else, depends on your operating system.
When getInput is invoked with this argument, this is the address. That means this p variable is going to be filled with the address of this in memory. Let's say that the address of product in memory is 0x05. Now the address of product pointer might be 0x10, for example. But the data that product contains is actually a pointer that points to a bit of memory that was a part of a call stack that is further down the stack.
Yeah, what getInput's product pointer there, what those 4 bytes contain, will be 0x05.
Yep. So this data, this value right here, is 0x05. That's contained within this product. That tells getInput where to access the data from. A pointer is a way to arbitrarily reference memory. And when I say arbitrarily, I do mean it. A pointer is nothing more than a memory address. That's all a pointer is, and that's all a pointer will ever be. Now, of course, pointers in C++, C++ being a typed language, are typed. Therefore, a product pointer is typed to a product. However, ultimately, at the end of the day, it's just going to be a single address. Can you make a pointer from a pointer? Yes, you can.
That will be later.
So by using the pointer, we are now changing the original product instead of the copy of the product. Exactly. By using this symbol right here, and this symbol being attached to a pointer, when we access this price field, we are actually accessing the memory inside of main. Or, to be more specific, we're accessing the memory inside of whatever function invoked it.
Marcel's other question is a key stumbling block in starting out on this. Can you explain the syntactical difference between foo, type asterisk, space var versus foo type space asterisk var?
In that particular case, there is no difference. There are differences in other situations. That gets into the dereferencing operator. However, there is no difference between these two. Remember that C++ is a white space insensitive language. So that is still a pointer. However, the asterisk operator used in different situations does provide a different thing. This isn't an operator in this context. This is think of it like an annotation on an existing type. Just like the array annotation on existing type makes an array of types. However, this asterisk can also be used as a specific operator called the dereferencing operator, but we'll get into that.
But Florum, it's not a question of which one you like the look of better. It will hurt you if you think of it that way. You can't just pick one. You can't pick which side of the space to put it because of the look of it. It can in other situations from this mean a completely different thing.
Or to get you used to thinking about the wrong thing, depending on what you're looking at. Okay, so
by using the pointer, we are now changing the original product instead of the copy of product.
Right.
Yeah.
So let's back up and talk a little bit about some of the operators. I'm going to delete the code out of main, but I'm going to leave the other functions for use later.
Oh, and I like Alan's question, but
how can it be white space insensitive, the asterisk being placed on one space? It's not a meaning to the language itself, it's a meaning to the person reading the language. The fact is, the dereferencing operator, the C++ compiler won't get confused on it because it's white space insensitive, but you will get confused on it because your brain isn't white space insensitive. So let's talk about some more stuff. So now I've got the sort of big example out of the way. The fact that we were able to do something by using pointers that we previously weren't. So let's back up and look at pointers at a simpler context. Because again, the thing about pointers isn't that the concept is particularly difficult. I mean, it does take some getting used to. It's more about a person being able to identify a problem solvable with pointers. And the fact is, you will be using pointers everywhere. Everywhere. Okay, so let's write some simple code. I'm going to say a number equals 10. And I'm going to see out a number. And I'm going to see out address of a number. This is the first operator that's important. The address of operator. You'll notice that when I print a number directly to the console, we get the value of a number, 10. But when I print the variable a number annotated with this unary operator, I get something else. This is the place in memory. This is the address. This is the zero-based index into how far into my computer's RAM it takes to get the data that a number contains. So if we do something like this, notice something interesting. Although these two have completely different values, if you look at their address, they're actually really close together. Fairly close together.
Ironically, 20 is earlier than 10 is.
Right.
Which is odd to me. But okay. Oh, that's right. This came up on Monday because your RAM allocates from end to beginning.
It's an operating system specific thing too. The operating system is free to allocate things in whatever way it sees fit.
I just think it's entertaining that it does it in reverse on your computer. And for those are, if you're not familiar with the maths side of things, those are hexadecimal. That's a hexadecimal number, base 16 number.
Mm-hmm.
And once you run out of numbers past 9, you use the letters A to F.
Mm-hmm.
So consequently, 28FABC is lower by C, D, E, F, G. So it would be 3 and 8, which is 11. Is 11 lower than the address of a number?
But you'll notice that
base 16 is basic. To paraphrase Tom Lehrer, base 16 is just like base 10, really. If you're missing 3 fingers and a toe. Sorry, carry on.
Okay. So this is the first operator. This operator converts any type into that type's corresponding pointer type. And if you were to display this number, you would get a literal memory address, which you'll notice actually is interesting in that there's a bit of a proximity when you're dealing with similarly located bits of memory, which is interesting to note, but not particularly necessary to understand. Well, it's necessary to understand, but not particularly useful in a lot of cases. How's everyone feeling about the address of operator? This is the address of operator.
Question that came in. How do you know when to use address of
versus
how do you know when to use address of versus the asterisk?
Dereferencing. We're going to be going over dereferencing in a second. So now let's talk about a number pointer.
I don't think that's what he meant. How do you know not to use the ampersand on line 12 instead of the symbol that you are using?
Because it's a completely different operator. This actually isn't even an operator. This creates a new type. This is saying the type of product pointer is not a product. The type of product pointer is, well, a product pointer. On line 22, the type of product is a product. 2 completely different types. And as you'll notice here, I've created 2 pointers now. These are pointer types. These are both integer pointers. The asterisk means nothing more in this case except for to annotate the type that immediately precedes it. My argument does use the asterisks, but in the context of a type annotation. Think about the difference between these things. What is P2? What type is P2? P2. Yep, it is an array of products. This is not a product. This is an array of products. Well, how do we know this? Well, we've annotated the type with something that changed the meaning of the type of this local variable to something else. In this case, the compiler does use both bits of information. It says, well, I know it's something to do with product, but then wait a sec, I also see this syntax being used. Therefore, I know this is an array of products. Whereas on line 30, we're just dealing with a product. Similarly, on lines 33 and 34, we are declaring 2 integers. These are unannotated integer types. That's all they are. But on line 36 and 37, we're declaring integer pointers. So just like how on line 31 we have an array of products, on line 36 we have a pointer to integer. So on line 12, this is not an operator. The ampersand in this context is going to be an operator. Now, I do really want to point out for anybody who's seen other C++ code, there is a thing in C++ called references, and C++ references actually recycle the ampersand operator and use it for a similar meaning to this, just to be incredibly confusing with how C++ recycles symbols. But in this context, I am using the ampersand as an operator. It's a bit of code that actually runs at runtime.
You can think of it actually as a method that takes in this case, a number and returns a pointer.
Right.
That ampersand symbol on each of those lines. If the method name was just ampersand and parentheses were invisible.
Right.
But you get my point.
And so this is not an operator. This pointer symbol is I don't know if this is the proper terminology if you want to go read through the C++ specification, but I feel that a very good way to express what this is an annotation to a type. We're modifying a type and turning it into another type by specifying a symbol. That symbol is not an operator. It's not a thing that's going to be run at runtime. It is literally creating a new type for us to use. Just like how we use arrays to create array types. We use the star or the asterisk to create pointer types. That's all it is. Okay, so on line 36 and 37, we create two integer pointers, and you know it's an integer pointer because it's the type int followed by an asterisk. We assign the address of both of our integers to this, Gavin?
Yes, indeed. Well done.
Okay, sweet. The whole English language thing kind of is annoying sometimes.
Words and things.
Yeah, stuff. We assign the address of the number and number 2 to the pointers a number pointer and a number 2 pointer. Meaning if we were to print a number pointer and a number 2 pointer, we would get some stuff. Actually, I'm going to go ahead and do a number address of a number pointer, a number 2, a number 2, a number pointer 2, a number 2, 2, a number 2 pointer. Then I'm going to add another one more. I'm going to say the address of the pointer.
You're not as elite as your keyboard.
Hmm?
I said you're not as elite as your keyboard. It's better than you. It knows where the buttons are if you don't.
Well, I have my tablet right in front of my keyboard too, so it's impairing my typing speed. So product pointer in the argument is the same thing as int a number, or is the first an annotation while the second is a pointer to an int? No, they're both type annotations. And again, I'm using the word type annotation. I made it up because it describes exactly what I'm trying to express. I'm using the word in the English sense, not in something that might exist in the C++ specification that I'm not aware of. But in the English sense, this asterisk is annotating this type and turning it into a pointer type, just like this asterisk is annotating this type and turning it into a pointer type. I'm only using the asterisks in one context in this entire code file. We're going to be talking about the other context that we can use it soon. But so far, I have not introduced the second context where that symbol is appropriate. We're going to be more appropriate if the asterisk is to the left of the pointer name. This code right here it kind of hurts my eyes. And it hurts my eyes for a few reasons. This asterisk, to me, when I'm parsing through this code, means a different thing. Now, the compiler will be able to figure it out. The compiler knows that this is a type definition, stuff like that. But if I was to parse through this code, this would confuse me, and this would confuse a lot of other developers, and you'll see why very shortly here.
Well, you just looking at line 36, it looks like you're declaring an int there.
Exactly.
And you're not. You're declaring an int pointer, the same as you are on 37.
Yep.
because the asterisk belongs to the int word there. It doesn't belong to
The name.
a number pointer. The name isn't asterisk a number pointer. The name is a number pointer.
Nope. Okay, so let's go ahead and run this code and take a look at it. So you'll notice a number is 10. The address of a number is, let's just say, D50. A number pointer is D50. And the address of a number pointer is D38. Same pattern can be found with a number 2. The pattern goes as follows. We get the value of the variable. We get the address of the variable. We get the address of the variable again. And then we get the address of the variable that's pointing to the variable that we got the value from.
And this should make sense, because you can see that's exactly what we're doing. We've got two numbers, we've got their addresses, and then the extra one is tagged on the end, which is the address of the pointer.
We have 4 variables on the stack frame of main. We have a number 2, a number pointer, and a 2 number pointer. Each one of these variables becomes resident in memory when the main stack frame gets pushed. As in, each one of these variables has an address in memory. However, the sole purpose of the variables on line 33 and 34 are to store the addresses of another variable, and that's why they're called pointers. Unless so take on night, can you explain why pointers need their own address? Why not refer to the address of the actual thing we are pointing to? They need their own address because they're variables.
So I just had a Goon Show moment. Everything's got to be somewhere.
Yeah. Pointers.
Although what they contain the address of something else in memory. But you have to remember, in order to store the address of something else, they need to take up some memory, which itself has an address. All of memory has an address.
Yep.
And in fact, can you go back to the whiteboard and then put that over the top of it?
I was going to actually do a completely new whiteboard to.
Good.
Very shortly here. I do want to introduce the dereferencing operator, and then I was going to go back and do a very comprehensive whiteboarding.
Okay.
Okay, so let's talk about one more operator. Is everybody at least... You don't have to understand this whole thing just yet. I am going to pull up a whiteboard, and I am going to talk about how this stuff relates to each other. But the important thing to take away from this are, so far, I've introduced 2 bits of syntax. I've introduced annotating a type with a pointer, turning it into a pointer type. And I've also introduced retrieving the variable, or retrieving the reference for any variable. Not the reference, but the address of.
Address.
Does everybody understand that so far? The fact that this is a pointer, and this is an address to a variable. How come int pointer didn't count the value of what was in memory address? How can you do that? I'm about to show the next bit of pointers. And that is the dereferencing operator. You'll notice it's a recycled symbol. It happens to be the same symbol that you use to annotate a type to turn that type into a pointer type. However, it's an actual operator that does stuff at runtime. It is an actual bit of code that will be, well, more specifically, it's an actual instruction emitted by the compiler to the CPU.
And like I was saying before, in the same way as you can think of line 45's ampersand as a method that takes in a number 2 and returns the address of it, you can think of the dereferencing operator there on line 48 as a method that takes in a pointer and returns what's in it.
Yep. So let's go ahead and run this code and see what we get. We should have some nice symmetry here, actually. A number is 10. The address of a number here is A20. A number pointer, the value of a number pointer is A20. the address of a number pointer is A08, and the value stored by the memory that is referenced here is 10. That's what the dereferencing operator does. So again, you get some nice symmetry.
If you take out lines 39 and 47 for now, it might make it just a little bit clearer.
Okay, so let's follow this backwards. Let's start with the last line and follow it up. Last line has the dereferencing of a number pointer. What does a number pointer contain? Or more specifically, what does a number point to? A number pointer point to? It points to the address 0038F9E0. That happens to be the address of another variable we have on the stack here with us. Specifically, a number. The address of a number is 0038F9E0. Meaning when we do the dereferencing, we loop all the way into this address and grab the value at this address, which is already being printed out here as 10.
Joseph, yes. It gives you the value at the address it is pointing to.
The dereferencing operator just reaches into memory, to wherever that memory is, and takes that value.
I like to visualize it that when you a pointer to something is like wrapping it in wrapping paper, and when you dereference it, you basically unwrap it again.
Yeah. So that's what this code is doing. And so let's jump back to the whiteboard and actually talk about this function and how this call stack works with it. Oh, come on. Okay. So main has an int a number and assigns it to 10. That's not a z. It also has an int pointer called a number ptr and assigns it to the address of a number. This is.
And Alan just asked, oh, sorry. I thought you were still writing. But Alan just asked, so it's like a double negative in the sense that you use it once to get the address and again to get the value.
Yeah.
Yeah, but note that it's on opposite sides of the word that it's attached to.
I'm going to quickly the memory. I'm going to just diagram out what memory looks like. Memory looks like this.
For those of you above a certain age, you will recall many happy hours spent staring at the old-fashioned Windows disk defragmenter, which I personally found quite entertaining. Does anyone know what I'm talking about?
Yeah.
There we go, dual op amp does. Well, that was really cool. And it showed you, presumably, just random gibberish. But, yeah, a lot of red blocks being picked up and moved around in your memory. And this is that, essentially. Or that was this, or vice versa. Yeah, I do. The new one's nowhere near as much fun.
You defragment your SSD?
Who does?
Do you? You really shouldn't defragment an SSD.
I never said I'd read you, I never mentioned SSDs.
Oh, I don't know. I just knew you had an SSD, and you mentioned defragmenting, and my mind is...
My C drive's an SSD.
Ah.
My D&E drives are Cows Blacks.
Okay, this is my made-up memory system. It starts at 0, and in this case it goes to, let's just say, infinity.
There are some bad bad sectors between 8 and 49.
I don't mean those as bad sectors, I mean those as...
No, I know. Just, sorry. I won't confuse things any further.
Okay, this is what memory looks like on our computers. It starts at 0 and goes up to however much memory you have. It's counted by single byte increments. You can randomly access any of those single byte any of those single byte values on your computer. And a pointer is simply a pointer to one of those boxes. So let's talk about how, if we were to invoke main, how the stack frame would look. Stack frame is going to look like this. And I'm actually going to do a more interesting diagram. I'm going to do a table. We're going to have everything in the stack frame has a type. I'm going to include the name as well. Although the name is not resident during runtime, I'm going to use the name to reference the source code. It also has a size, and it has an address, and it has a value. Everything on our stack frame has these attributes. So let's talk about the attributes of a number. What is a number? Well, a number is an int. It's called a number. It's 4 bytes wide. And let's say a number is this box right here. More specifically, a number is this box, this box, this box, and this box. This is a number. Meaning the address...
4 bytes of memory.
4 bytes of memory. Meaning the address of a number is in my imaginary addressing scheme is 0x50, and the value inside of number is 10. This is memory. This is your memory. This is the memory that you see when you open up your task manager and go to performance. This is memory. So when I say memory on the right-hand side, that's what I'm referring to this. However, this stack frame is an aspect of memory because the stack frame is loaded into memory. Everything that's in memory is in memory, and stack frame is in memory. Anyway.
I'm sorry, I was still dealing with the fact that you've got like 9.38 gigs of RAM in use. That's just ridiculous. Anyway. Hello? Nelson?
Oh. See, I hit the stupid button on my microphone again. How much did you miss?
Since you started writing the current line you're on.
Okay. Okay. I want everybody to guess this value and this value. Just comma separate them. Actually, the address itself is irrelevant. You can pick whatever number you want for that.
I was going to say.
Okay, for the purposes of this explanation, and to avoid confusion, I'm actually going to place this value on the stack here, I'm going to place it on 0x56. So that's 1, 2, 3, 4 bytes. The address is 0x56. The value is 0x50. Now the value is what's important. I do want to point out for some people who guessed that the address of this would be 0x51, that would be impossible because the address of data in your memory is going to be the first byte that it consumes. So the address of a number is going to be 0x50, even though it takes up 4 bytes of memory, and the address of a number pointer takes up 4 bytes of memory over here. So this is a number. And this is a number PTR. I do want to point out, just for the sake of completeness, that there does exist a construct in C++ and I believe C called a union that allows you to have multiple variables taking up the exact same bytes of memory. But that's irrelevant to the discussion. I don't think I've ever used a union for anything. It's a stupid idea. Okay.
Dando, remember, pointer size is dependent on your operating system and on what it was compiled.
Yeah.
Yeah. But the point being, it's a coincidence that it happens to be the same. It's just because he used an int in this case. If it was a string, that wouldn't be 4.
Right.
But the pointer would still be 4.
So what does this do? What does this code do? This code takes the value of the pointer and uses it to reach into memory at that specified location and then grab the value that's stored in that memory. The value that's stored in that memory happens to be 10. So if I was to draw the diagram in a different way, I could say 0x50 points to this variable on the stack frame. Because it points to this variable in the stack frame, the value is 10. And as a result, this prints out 10. And it prints out 10 because it's reaching in to the value of another piece of data that is somewhere else on your computer. Is there a way to set the size of a pointer? No. Size of the pointer is determined specifically during compilation. It's determined by your compiler.
No, he said to see the size of a pointer. You shouldn't be looking at that anyway.
Oh, see the size of a pointer. That's going to be a size of operator. Are there any questions about this diagram? This is so fundamentally, ridiculously, stupidly important. And I really want everybody to understand it. So if there's anything else that I can backtrack on, please let me know. Okay, let's introduce another thing, just for sake of completeness. Again, some people, a lot of beginner books on C++ do not have a discussion about what I'm about to talk about until later on. But I want to discuss it right now. The reason I want to discuss it right now is I think that it's very important to understand that pointers are just that. They're pointers, and they can point to anything, including other pointers. And hopefully, by showing what I'm about to show, it will solidify some understanding. I'm going to add another line of code here. An int pointer pointer. I'm going to call it a number PTR PTR. And I'm going to assign it to the address of a number pointer. So let's start off with this. Int pointer, pointer, a number, pointer, pointer, 4 bytes. Let's say that the pointer exists, let's say...
Put it up in the top, memory up the top that you've got spare.
I do kind of want to keep these near contiguous, just because it might interfere with our discussion later on dynamic memory.
In that case, draw some more boxes. Haha. Otherwise you get an out of boxes exception.
A number, pointer, pointer. Int asterisk asterisk means a pointer to an integer pointer. The address of a number, pointer, pointer, in this case, again, is arbitrary and up to the implementation of the compiler and or the runtime, but in this case, I am going to place it on 0x61 on my imaginary addressing scheme. The value, what's the value of a number, pointer, pointer?
Rolling Stone should answer that. Well, you were asking for something to work on, so...
The value of the pointer pointer in my imaginary memory address scheme is going to be 0x56. So if I were to do cout, dereference, dereference, a number, PTR, PTR, what would happen is we would start off by dereferencing this. What happens when we dereference this? Well, we jump over here into this box and we grab its value. What's its value? 0x50. So that's the first dereferencing. The second dereferencing is going to grab the value right here, jump into memory, find the value stored at that memory address, and then return it. So the second dereferencing operator is going to return 10. So remember, this dereferencing operation returns 10. This dereferencing operation returns 0x50.
And remember, it's just because, I mean, he happens to have done dereference twice there, but he could quite easily have, on that cout line, just have done one dereferencing, and in which case it would have outputted 0x56.
No, it would have. It would have outputted 0x50.
Sorry, yes, the value of 0x56. And yes, somebody said, how far can you go with that? And the answer is way too far. But yeah, I'm with Rolling Stone. We've been going for coming up on an hour now. It's time to give them something to do, and so that you can go off and relax.
Based off what I have on the screen, recode the example that I had previously, allowing the user to... I will give the definition of the struct out.
Mr. Perlishell's put it beautifully. He said it's like fishing for fishing poles.
That's funny. Based off what you have, what you see on this screen contains a reference to every bit of syntax you need to accomplish this goal. With the exception, of course, of that guy. Recode the example that I have and allow the user to create a function that accepts a product pointer. Yes, I forgot the semicolon on the struct. words. Create a function that accepts a product pointer and fills it in with info from the user. Then invoke it from main and pass in the address of a product variable that's on the main stack frame. Does that make sense for everybody?
You're going to have to write that out. Or at least type it out, yeah.
Why am I worrying about capitalization?
It's hard to tell what you are because we can't see it.
Do this. From memory, or at least based off what's on the screen right now. Okay. I'm going to go ahead and pause the video. And we're back.
Hurrah!
So the prompt really was to get people to actually go out and type some code. However, I have already typed the code. And this is what the code would look like. And then given an invocation from main, it would look like this. How many people here have had no introduction to pointers before the class started? How does this code, specifically lines 30 and 31, and lines 12 through 20 look now? The indirection operator basically is the same thing as this. So product pointer name is the same thing to dereference product pointer and then dot name. It's the exact same thing. It's simply a nice little shorthand that C++ gives us, and C as well. So we can access, or not C, because C doesn't have members. Or yes, it does, it has members on structs. Keep on forgetting the differences between the two. Anyway, so you'll notice here that we are accessing a member within this object, but via a pointer of that object. We're doing the same thing here, but just in a little bit more verbose way. We're dereferencing the pointer, and then accessing it via the general member accessing operator. Yes, it's essentially the same thing as product.name if product was not a pointer, if product was simply a product.
Well, if product was what resided at the memory address that product pointer points to, specifically.
Yeah.
So, cool.
Okay, so just for completeness, let's go ahead and really quickly talk about the string table. And I do kind of want to actually point out this example one more time, where now that we have the table, well, for some reason I still have this code running. Now that I've looked at the table, this should hopefully be a lot less intimidating. Dereferencing, address of a pointer, address that the pointer is pointing to, address of a variable, a non-pointer variable, and the value of a non-pointer variable. So let's go ahead and nuke this code and talk a little bit about strings. So let's say I wanted to fill a product array. This is really just a fun little aside that a student in Monday's class accidentally stumbled on, which I thought was a great thing to quickly talk about. You already know what I'm doing, right, Gav? Does any bit of this code, all of this code makes sense, right? It's clear what I'm intending to do, right? What do you think the output of this program is going to be? Well, I mean, I guess I can go ahead and run it. I'm going to just display the product name. I'm not going to worry about displaying the product price to make the example a little bit clearer.
Oh, this one. Yes, sorry. I'm with you.
In fact, I'm going to up the array size to 20. I'm going to up the array size to 30. I'm trying to grab some more memory here.
Hurrah.
Actually, I think what I can do is
write more in it to start with.
Yeah. What's going on here? Line 33 on the first iteration of the loop results in product. Second iteration of the loop results in product. Third iteration of the loop results in auduct. Fourth iteration of the loop results in duct. Fifth, uct. 5, t, and finally 6, t.
Then things start to get silly.
Yeah, then things start to. It depends on so many other factors what is going to happen afterwards.
Didn't you grab like 100 afterwards?
Yeah, let's try 100.
You said it had to be 100 starts on Monday.
I hope this doesn't throw a access violation. Oh. Then we have invalid string position, valid string position, valid string position, alid string position, lid string position, id string position, d string position, and then so on and 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 so on.
On.
This code actually makes complete sense. What's going on here is I did mention this earlier when we were talking about strings. A string literal in C++ and in C is nothing more than a character pointer. That's all a string literal is. It's a character pointer, specifically a const character pointer. But constness and pointers are actually really complex. I'm not going to get into constant pointers. But what we have here is a basic example of some pointer arithmetic. This gets turned into a character pointer, and then we add I to it. Meaning the first iteration of the loop, it's going to point to where the compiler placed this string literal, and then one item or 0 items forward. And then the second time it's going to do 1 item forward, and 2 items forward, and 3 items forward, and so on. So what's going on here is when your program gets compiled into the assembly that it is, into the, sorry, not assembly, but executable, you have something called a string table. A string table gets loaded into memory, and it'll have every single constant string located within it. So for example, it will have the string product. Also, this particular string table in the example that I showed had an invalid index or something like that?
Yeah, something like invalid string position or something. Don't know, can't remember. This would also have things like, hello and welcome. This would have, it looks like you're trying to write a letter. Would you like some help?
Mm-hmm.
Any literal strings that you've got.
Yep, and your entire program get placed into the string table.
And this is, I mean, why would be a good place to start. Why is that?
Well, I mean, that's just how it works. I mean, are you asking why character pointers are strings or why we have a string table?
Why we have a string table?
Efficiency reasons. Because instead of the C++ compiler emitting a bunch of instructions to make a piece of data equal to a string, instead it can represent things as a string pointer. Or a character pointer, sorry. And the character pointer will point to the first item within the string table that it appears. Also, strings are recycled, meaning that if I have two product literal strings, I'll only have one entry in the string table called product.
And two different pointers to that. I mean, two different things pointing to that.
Right. So when I say something like name equals product, I am saying name, if it's a character pointer, is now pointing to this thing. Now, when using the string object, it's a little bit more involved. The string object overloads the equals operator and will make it so that the string literal passed in on the right-hand side is copied into the string object's memory. But the same thing, it's the same thing. We get a pointer to this character. When we say name equals product, or sorry, I didn't mean to terminate that. Product plus 2, we are getting a character pointer to 0, 1, 2. We are getting a character pointer to O, which means if we tried to print product plus 2, we'll get a string that looks like this.
And if you think back to the picture that you, wherever it is, with all your row of boxes, column of boxes.
Yeah. Like, in the case, this would like be P, this would be R, this would be O, this would be U, this would be C, this would be T.
You'd have missed a D out, but yeah.
You missing what?
D after the O.
D.
4 should be D.
U, T, blah, blah, blah. You get the idea. By default, the string pointer, the character pointer is going to point to this. If we move it 1, 2 items in the future, we're now pointing to the O. And when we try to print this out, we get product. Or sorry.
Incidentally, assuming that the string just said product.
It's the other way around. It's one more.
Nelson,
what?
Can you hear me?
Yes.
Assuming the string just said product, go with me on this, what would be address 0x08?
Oh, right. 0x08 will actually be the null terminator.
Mm.
So then when we're pointing to C, we print out until we reach the null terminator, which will result in product. I do want to point out something that someone pointed out to me, and I realize I totally messed up with this diagram, and to anybody who also noticed this, do not think I am this stupid. However, although I am using the OX prefix for everything, making it look like they're all in hexadecimal, I kind of actually didn't represent it in hexadecimal.
You just kept drawing in decimal numbers.
Yeah.
But, you know,
It's
it makes the example easier to read, to be honest.
Yeah.
And the key thing is they are all valid hex numbers.
True.
It's just you've missed out everything between 10 and 16, 20 and 32, whatever it is, 24 and 32.
Is everybody good with why we're getting this strange output from this program and why it makes complete sense?
Excellent.
Okay. So I think we're going to be talking really quickly now about dynamic memory allocation?
Woo! Are we going to be doing that forte or piano? Whoosh! Sound of a joke going low overhead.
All right, this stuff is definitely going to be the fun stuff. Actually, no, not yet. I'm sorry to get your guys' hopes up, but there's one thing that I want to talk about really quickly. And Florin, we'll be talking about arrays as pointers after we discuss dynamic memory allocation. Let's talk about a problem.
Global warming?
No.
House ending?
No.
Dual op-amp spelling of humour?
No. Can anyone tell me why this code... Actually, this is going to be fun. I have a great idea. Come on.
Well, you destroyed your syntax on line 39. What are you doing?
Oh, derp. Can anyone tell me why the result of this program actually does make sense? And can everybody see immediately why it's happening the way it is? I should have asked this as a question, but still.
You just did.
No, asked what the output should be. But can anybody see why this output is incorrect? And can anybody explain to me why the actual output does have a very sensical reason as to why it's working the way it is?
Did you just say sensical? That's fantastic.
Oh, whatever.
No, it's just I've never heard that used before, but there's absolutely it must exist because you have nonsensical, so you must have sensical. So that's brilliant.
Can anybody say why the value is 20? Notice how I get a product that's 10, and I'm going to see out it. I'm going to print the price immediately afterwards. Well, with a new line. And I can do this all day, actually.
And he will.
This product pointer never changes. The product pointer is constant, and we only assign it once. However, by invoking the function repeatedly, we are getting bizarre results. Now, what about this? I'm going to take the string name out of product for now.
Just keeps it clean.
I didn't align quite right. Either that or... it optimized it out. Nah, it didn't align. But anyway. Look at this code. I'm not altering P at all. But, if you'll notice, the output that I'm getting for price is altered every time I invoke the getProduct function, and is also altered when I invoke the blef function, in this case to an invalid result. Actually, I think I could get it to align. I did this. Yes. And then when I do ble 4, when I say double temp equals 10, which I don't even think I have to return to get this to work right. Yeah. Everybody see what's going on? I invoke ble, and a local variable within that function is getting assigned to our price field, without the price field in any way directly being altered.
That's mental.
Yeah, it is.
Yeah. You going to draw that out?
Yes. When we invoke getProduct, so here's the stack. First thing we do is we invoke main. Main includes a product pointer. Then we invoke getProduct. Product has a product on the stack. However, the address for this product, which let's assume is 0x50, is getting assigned to the pointer in main. So now the pointer points to, in main, points to 0x50. But here's the problem. When getProduct returns, this memory goes away. Now the next time we invoke getProduct, we get another product on the stack. This is going to be on the same memory location. So,
and of course, it's going to be the same size as well.
Yep. When we call ble, ble has two doubles. Which happens to align with this stack frame, causing this double to point to 0x50. So after this gets done, ble is invoked. This double in ble happens to have the same memory location as what main, the product pointer in main, is pointing to, meaning it gets overwritten again. I think everybody in BuzzNet has already been like summarizing what I've been saying, so I assume that pretty much everybody's getting it. This is not a buffer overrun. This is called a dangling pointer. A pointer that's pointing to memory that is no longer considered to be valid and has been overridden for some reason.
It's like a letter for the previous owner.
Happy bug hunting with this. Here's the lesson. Never,
don't do it.
ever return a pointer to a value that is allocated on the stack. Ever. In fact, I believe I got a compiler warning from C++ telling me what I was doing is stupid. Yep, returning address of local variable or temporary. Watch out for this warning. This warning is incredibly important. This is saying we are returning the address of something that's going to be de-allocated very shortly. I assume this makes sense to everybody. It is pretty straightforward once you can conceptualize how the stack works.
People seem to be good with it.
Okay, so... Oh, right. I'm not in Photoshop. I can't use my eraser in Visual Studio. You can create functions that return pointers, but you shouldn't return a pointer that points to something that was allocated on the stack frame of the function. So let's talk about dynamic memory allocation. So far we've discussed the idea of a pointer, and we've seen a very valid use case for pointers. in regards to the stack, where we have been legally allowed to reach into another stack frame and alter data from a function that's further down or further up the stack. Great functionality that's very commonly used. However, the actual biggest reason that pointers even exist and are so incredibly important is the concept of your program requesting additional memory from the CPU during runtime. That concept is so incredibly fundamental to virtually every problem you ever wish to solve in programming. Now, sadly, a lot of languages make dynamic memory allocation a trivial task that people don't even care about anymore. But we were allocating memory dynamically in week 1 of the C# 101 or something like that, and you do a scripting language, you're going to be allocating dynamic memory the second you type something into it. But in C++, we had to wait till week 6 because there's quite a bit of prerequisites in order to understand what exactly is going on. Hopefully this is going to make sense now that people have the background, especially of pointers. Because not surprisingly, if you conceptualize the process of allocating additional memory, you need a language feature to be able to reference that memory. And that's what we've been discussing pointers. Pointers can point to anything in memory. They can point to things that are on the stack, they can point to things that are on the heap, they can point to memory in different processes, they can point to protected memory, and of course get an exception if you try to dereference that pointer, but still. Pointers could technically point to memory that you don't even have on your computer. Of course, again, when you dereference that pointer, you will get an exception. So, how do we allocate memory?
And if you know any C#, forget it.
Yeah.
For this point, seriously, don't think about C# in any way, shape, or form.
The new operator. The new is an operator in C++. In fact, it is an overloadable operator, which you can do some fun stuff with that. New, basically what new does, so let's go ahead and talk about what new does. I need a bigger, oh, come on. Don't be like that. Give me my brush size. Make it bigger. Okay.
Square brackets change brush size.
I have a little dial on my tablet. See, I can change what it...
Yeah, but it's easy. You're probably quicker at getting in the square brackets. Anyway.
So pointers are used every time memory allocation happens. I want to be technically correct here. Dynamic memory allocation has absolutely nothing to do with pointers. However, if you want to use the memory you've dynamically allocated, you must use a pointer. So let's talk about what that code does that I previously wrote. Int pointer number equals new int. This is the stack. This is the heap. And we have been sort of alluding towards the heap all throughout the course. And let's finally define what the heap is. The heap
is not the stack.
Is not... Essentially,
there you are.
Essentially, that's what it is. The stack is memory that's made available to your program by the operating system. And typically it'll be contiguous, although that's not even required. Operating systems can do whatever they like. But the stack is something that's made available to your program, and your program uses for local variables on your functions or methods. The heap is every bit of memory that isn't in the stack. The heap is a place in memory that you can request the operating system to give you dynamically during the execution of your program. So what do we have here? After this line of code executes, what we have is an int pointer on the stack. and then we have an int on the heap.
You should do this with doubles instead.
I was actually about to.
I'm worried at how much of this I understand. I really wasn't expecting to, but I keep being able to explain things and see things like that.
Maybe it's just my awesome teaching.
That seems unlikely, but let's roll with it. Are you going to ask the question now?
Which question?
Phrase it as a question. The reason why we changed that.
Oh, yes, okay. So, how many bytes on a 32-bit process is going to be allocated for the stack? And for the purposes of this explanation, the stack of the program, that we're assuming that we're in the main stack frame, and this is the only thing in main, of course. Stack frames do contain more than just local variables and parameters, but still. How much memory is allocated for what I have represented here in the stack, and how much memory is allocated with what I have on the heap after this line of code executes? The stack built on Visual C++ for a 32-bit process will result in 4 bytes on the stack. The heap will get 8 bytes. That's because all this pointer does is it references or points to data that is living on the heap. This double pointer is assigned to the result of the new operator. The new operator looks at the type that we're newing up. In this case, we're newing up a double. A double, on my computer, is 8 bytes. New knows that it has to allocate 8 bytes, so it asks the operating system for 8 bytes. So here's the OS. New asks the operating system for 8 bytes of additional memory. The operating system then returns the address of the memory that it allocated. And by return...
No, again.
You what?
2 Ds in address.
2 Ds in address? Oh.
Wow.
Yeah, anyway, it doesn't matter. Is everybody understanding what this diagram signifies? So I'm guessing using the concept of pointers to look at memory on the heap makes the executable run much faster. The performance characteristics of using pointers and dynamic memory allocation are a little bit more complex than what you might expect. Dynamic memory allocation and dynamic memory de-allocation, which we'll be talking about soon, is a relatively expensive operation and should be done as few times as possible during the runtime of your program. Obviously, many programs that allocate memory many times, and you shouldn't really worry about it. However, if you do, for example, have a game loop, you wouldn't want to be instantiating a considerable amount of things during a game loop that's supposed to run every frame. That memory should be pooled. It should be allocated in a giant chunk, and then bits of that memory should be split across to the things that need it. That's typically a more appropriate way to handle memory when working in high-performance situations. However, when you pass a pointer to an object or to a function instead of an object to a function, you will get typically you'll get better performance code because let's say you have a structure that's 128 bytes wide. Obviously, passing in a 4-byte wide pointer is going to be significantly faster to do. But this is such an important concept This is how we can ask for more memory from the operating system. Ridiculously important.
And remember, because, for instance, if you're using any sort of graphics application, you will be dealing with a very similar situation whereby you have your page files and such like. I mean, nowadays you can have as much memory as you want, as much memory as you've got space for on a hard disk.
Yeah.
You can use that. That could be, and I quite like that example because, you know, if you think about all your program files on the C drive, but then they pass off to however much space wherever you've put it on your computer. It can be on an external drive, it could be in the web.
Yep. Should you use any special casing to differentiate pointers? And you should absolutely not. Casing and naming conventions apply, or should apply, at least in a perfect world, where I get to govern everybody's software engineering practices.
And I get to govern their spelling.
Yeah. Everybody, the only difference between different casing and different formatting and naming conventions should be determined by the member, the member or the variable, the accessibility of the member or the variable, and the staticness of a member or a variable. And that's it.
And if you think about it, you've already got some special syntax that enables you to differentiate it as being a pointer.
Exactly.
You've got the asterisk being used.
Okay. So let's go ahead and run my code. What does everybody think is going to happen when I run this program?
The end of days. Oh, did you see Jeffrey's question, by the way?
So pointers are, yes, and I answered it. Okay, let's fire up my nice little task manager and watch my program as it runs and see what happens. This is called a memory leak. A memory leak is when you repeatedly, or not necessarily repeatedly, but you continuously throughout your program ask for more additional memory from the operating system, and you don't give it back when you're done. Now, it's not, that's pretty much the definition.
It's just rude.
Yep. Oh, and you notice that I have exceeded how much a 32-bit process can address on my system, and I get an unhandled exception. Of course, if I compiled this for 64-bit, it would actually probably eat up all my memory. This graph is very interesting to note. You'll notice that I continuously allocated more memory from my system until it reached 2 gigabytes. And when I reached 2 gigabytes, it stayed alive for a second as I was sitting in my debugger, and then it dropped. Windows will reclaim any memory that your process has allocated during your process's execution. So you don't have to worry about destroying your computer without, or permanently without having to do a reboot. But you do have to worry about, during the execution of your program, exceeding the limits of the process. So how do we de-allocate memory? Is that equivalent to the size of the operating system's page memory? No, it's the example that I showed was the limit to how much memory a 32-bit process can address. A 32-bit process may only address 2 gigabytes.
Is that just an arbitrary number they pulled out of thin air because that was about as much memory as seemed sensible at the time they invented it?
Well, it's funny because
it kind of feels like
you can address up to 4 gigabytes with a 4-byte pointer. So I'm not necessarily really sure about the history behind.
Okay, I just wondered
why
that's the
that's
sort of thing that you might have known.
It's an interesting question. But anyway,
But dull answer.
Now let's watch our program. In fact, now my program is using the least amount of memory from every single other process running on my computer. Of course, it's still eating up my CPU.
Which kind of makes sense.
Yeah. Of course, it's still eating up the CPU. But, yeah. Actually, I'm curious. This is just for my own curiosity. 396, 396, 396, 396, 396, 396. Huh, that wasn't terrible. That was only 30K. Okay, so you'll notice that my program is continuously allocating 4 bytes of memory, then deleting it. The delete keyword, or more specifically, the delete operator, which, again, delete is an operator. It actually runs, it's not a keyword, it's an operator. Well, it is a keyword, but it's also an operator. It actually runs code that you can override the behavior of, if you were ever so inclined to. Actually, what's going on behind the scenes is the functions malloc, malloc, and free, which are functions that come from C, are being invoked. Just a little bit of interesting tidbit of information. Anyway, the delete operator will inform the operating system that you are finished using the memory that you asked for. So this code will continuously allocate 4 bytes and continuously free 4 bytes over and over and over again until infinity. You should always pair up a new with a delete. That's incredibly important. If you don't pair up a new and a delete, then you will run into a memory leak.
To paraphrase my incredibly long spiel from Monday, it's always a good idea to do essentially what Nelson's done here. It doesn't matter if anything is going in between lines 5 and 6. Do your new and then immediately put a delete and then go back and fill in the gap in between. It will instantly save you a lot of grief when you're learning.
Yep. Okay. I'm going to go ahead and put us on break, but I do want to put in a little prompt.
Do you understand the question that's just come in?
Isn't 8 instead of 4 on every pass? Isn't 8 instead of 4 on every pass? Isn't 8 instead of 4? No, we allocate 4 bytes of memory. Did I say 8 bytes of memory? I meant 4 bytes of memory. An integer is going to be 4 bytes wide, at least on my operating system. Or at least my implementation of the C++ compiler. Alright, so I'm going to go ahead and pause the video, and we are back. So let's go ahead and type out what this code will look like.
So someone did ask while you're typing, is from where does he deallocate the memory?
Inside of main is typically what you would do with functions that return the dynamically allocated pointer.
Would it be... I mean, really, the answer should be as soon as you're done with it. Put the toys back in the box when you're finished playing with them.
Yeah.
And then your room won't get a mess. I'm sorry, I just flashed back to being 6, but the point stands. Really, well, think about it. It's an optimization point, really. You have only got a finite amount of memory on your system. So really, if you're not using, even if it's only 4 bytes, it soon adds up. And once you're done with something, you should deallocate it so that it can be used again for other stuff. And yeah, Rolling Stone pointed out that okay, it would be in the destructor, but that would involve having a class which doesn't exist. I've never heard of a class.
Yeah.
They don't exist.
Sweet. I do want to point out that delete will invoke the destructor of an object. But, again, I don't know what a destructor is, and I don't know the words I just said. They just came out of my mouth.
Fish.
So we can use them instead of using global variables. Yes! You would use a pointer to a common piece of data as a parameter to functions instead of using global variables. Okay, so let's talk a little bit about arrays and pointers and dynamic memory allocation. Let's first talk about passing a pointer into a function, because now we have the necessary understanding to do so.
That was passing a pointer into a function.
Passing an array into a function.
You said pointer.
They're the same thing.
I know. Well, you corrected me, and you were wrong. One item free.
I
said one item's free.
Yes. Okay. What we have done here is we have successfully passed an array into a function. A product array is very, very, very similar to a product pointer. In fact, if you'll notice, I changed the symbol of a product array into a product pointer, and the code still just works. The fact is, these two symbols are virtually synonymous, and they mean pretty much the same thing. We are passing in a pointer to the first item in the array, and then we're giving the array a count, or the method a count, the function a count. Words. Anyway, here's the code. Do you understand it?
Well, no, I was just thinking the best example of that is the one where you build a for each loop. The actual parameters of the loop. So you're doing the beginning and moving and so forth.
You mean the vector?
Not exactly, but I can't think. I just can't think.
Can't think. Gavin can't think. I can't think. Class is over. Okay, so this code is basically allowing us to pass an array of products. We use this symbol right here, and it's virtually synonymous with a pointer. In fact, there exists an implicit conversion between a pointer and an array. So let's talk about dynamically instantiating an array. Dynamically instantiating arrays is a little bit more complex. I kind of feel mean for asking this, but what is the output of this program? The The reason I kind of feel mean is because I am actually demonstrating a bit of syntax that we haven't covered yet, but it is something I want to drive home. When arrays and pointer, why does this work and not that? That's because the indexing operation of an array is an automatic dereference. It automatically dereferences the value. Instead of you having to increment the pointer X amount of times and then do a dereference, that's essentially what the index operation does behind the scenes. Okay, now that I've had a bunch of people staring at this code and wondering what the output's going to be, watch what happens when I run it. We get a nice little error.
Well, that's clear.
We get a blocked
Dumb error.
type is valid assertion failure. What's happening is, when we instantiate something and use this syntax in order to instantiate an array, this isn't a normal pointer. It's a special type of pointer, an array pointer. And it actually adds a little bit of more information to when doing the instantiation, which means that the delete operation must be paired with the proper... The delete operation isn't valid for this type of instantiation, is what I'm saying. Although the types are the same, the delete operation isn't valid. The reason the delete operation isn't valid is because this is a fundamentally different operator than the original new keyword. And it's different because we've specified a number right here. Just like you have to pair every new with every delete, you have to pair every new type with a number to every delete bracket bracket. This is a completely different operator than the other delete keyword. And this is what's supposed to be used when deleting a dynamically allocated array. This will bite you. It will. I'm not kidding. But now you'll notice that if I run this program, I don't get that error anymore. Remember, every new goes with every delete. Every new array goes with every delete array. So let's go ahead and build a dynamically sizable array.
So you see what Flora put?
Me climbs on the desk as to not get bitten.
That's very funny.
The brackets must be immediately after the delete. This is an entirely new operator. I typically format it like this, but I won't hold a grudge against you if you format it like this. But I will generally do this. Okay. So let's implement a dynamically resizable array. And the dynamically resizable array will be very similar to the functionality that we get with the vector class. Now, the vector class is a little bit more intelligent than our dynamically resizable array implementation, in that it's a lot more performant than what we're about to do for a variety of reasons. But let's go ahead and build out a very naive implementation of a dynamically resizable array. I'm going to start with a products pointer, and I'm going to set it to null. Now, we haven't talked about null yet. Null is a special value that all pointers can be assigned to. Now, you might be saying, oh, Nelson, null is actually 0. Well, yes, null is 0, but null itself, the concept of nullness, does not in any way relate to the concept of numbers. A null is basically a flag. It's an initialized pointer that doesn't point to anything. And you can check for null by using the null constant, which is null in capitals. So let's go ahead and build a while loop that will allow a user to insert many products in as many products as they wish.
missed the word "or" out of your prompt, but no need to shout.
Okay. Oh, right. I never put in a prompt for price.
So
I've just written code that allows us to enter as many things as we want without using a vector. So let's talk about the implementation. The implementation is fairly straightforward. We start off with a structure product that has a string name and a double price. Again, fairly standard sort of example-y stuff. Then inside of main, we create a products pointer and we assign it to null, signaling that the products is null. Then we say unsigned int products count and assign that to 0. So our products count is initialized to 0. We enter an infinite while loop, and inside the loop we first declare on the stack a temporary product to store the data that we are going to be entering into the program. We enter a prompt that says enter the product name or blank to end. We get the prompt, we check to see if they entered blank, in which case we break. Then we have them enter the price, we grab the price, and we ignore the new line. This code should make perfect sense to everybody so far. The fun
now we get to the interesting bit.
Is between lines 30 and 48. The first case we have to handle is the first product that we enter. So I'm going to say if products equals null, then assign our products pointer to a new product array with one element, assign the only item within the array to the temporary product variable that we've created, and set our products count to 1. That's the first case. Now, we have to do a little bit more work, however, if products is not null. So the second iteration of the loop, what we're going to do is we're first going to create a temporary variable to hold our old products array. And then we're going to instantiate a new array with one additional item and set that to our products pointer. After that, we are going to run through 0 to the amount of products that are in the old array, and we will copy them over from the old array to the new array. Then at the end, we'll assign that new empty product entry that we've created for ourselves with our new instantiation of the array to the temporary product that was created. We increment how many products we're keeping track of, and then we delete the old array entirely. So by doing this, we ask for more memory every time that the system, every time the while loop runs, to an unspecified amount of time. Why must you do the first part of the if statement? Why not just run the else part only?
If, well, the first time through, what is before, at line 31, what is products?
And the answer is null to everybody who seems to be asleep right now.
It could just be lag. We're going to see a whole load of nulls come in a minute.
Okay.
It does, because the first time through, yeah, do you want to just explain the answer?
Yeah, the first time through the loop, we're going to be setting our products array, or our products pointer is set to null, signaling that no memory has been allocated for it. So that's a special case where we have to take care to go ahead and instantiate the first chunk of memory for a product. If we had tried to run the code that's in the else statement, we would get a lot of errors. The first error that we would get is, well, actually we really wouldn't get any errors until we deleted temp. Everything else would run fine until we deleted temp. The for loop wouldn't run because the products count would be 0. This would work, but then we would delete temp. And the problem is that temp would be null, because if you notice on line 38, we set temp to equal products. And deleting a null pointer causes a runtime exception.
Does that make sense? Whomever asked about that. Cool.
Okay. So let's one-up this example just a little bit. Let's turn our products dynamically sizable array and turn it into a structure with a bunch of other methods, or sorry, functions that work with it. So I'm going to create a...
Someone did ask, is null a CPP keyword?
No.
And I'd just like to point out that it isn't. But also, the null that we're talking about isn't the same as the one that you wrote, because it's null in block caps.
Yep.
And I know that sounds pedantic, and it is, but if you don't do it in block caps, it's not the same thing.
Nope, it will be nothing, actually. We'll get an error.
I wasn't sure what would happen, so I just deftly sidestepped that.
Okay, so what I've done here is I've factored out some functionality into separate functions.
Do you want to just split that? Do you want to just split that across so you can see all the code at once?
Let me use it first.
Oh, yes, that would help.
People who are used to C will be very used to this style of coding. Line 40 shows an error. Line 40, 40, 40, 40, 40, 40. Oh, right. Let me just run this to make sure it still works. Sweet.
Did you see what Florian said?
Yes, hovering over null will produce a define 0 in Visual C++. However, that is not guaranteed to be true for every single compiler. And again, it is a constant, but it shouldn't be treated as if it were a constant, because it is a special value, a special case of a value that all pointers may have. How does everybody feel about this code? I created 3 functions: init, inventory, add product, and delete inventory. And these 3 functions abstract away the actual dynamic memory allocation. So you'll see here on main, line 57 through 87, I'm able to simply use my inventory abstraction and clean up my code significantly. If it can't get memory, does it return null? If newing up something can't get memory, it'll throw an exception. It won't return null. Is this not just a vector? This is how a vector is implemented at a very rudimentary sense. A vector, again, has a lot of more functionality and a lot of additional optimizations. However, this is how a vector is implemented, using the concept of a dynamic memory allocation, which makes it a decent example to show people about how you can use dynamic memory allocation, structures, and functions together to make your code do something interesting. So when I call pushback, is it similar to add product? Yes. Again, it has some more optimizations. For example, when you reach the capacity of the internal array that a vector uses, it will actually allocate another array with twice as much memory in it. And then when you continuously invoke pushback, it won't have to redynamically allocate memory every time you invoke it. It'll simply fill up its internal buffer until it's reached the end again, in which case it'll do the same operation. It'll double how much memory it uses internally.
Because basically using what will be relatively a small amount, even when it's quite a lot, but when you're using more memory, is going to be far more performant than using more CPU cycles.
Yep. And I do want to point out that this is how the C# list class is implemented as well. Again, in a rudimentary sense, it has more optimization.
This is conceptually what it does, essentially. It won't be using the exact same
Right.
calls. It will be doing it in a more optimized and obscure way.
Also notice that I'm taking advantage of passing in a pointer to an object from the stack. If I were simply copying the inventory to the init inventory function, then init inventory would get a copy of inventory and wouldn't be able to edit those values. Okay, I'm not seeing any more questions, so I assume everybody is either completely lost, asleep, or understands what's going on.
Two people are lost. A-Shields completely understands and is lost. Yeah, I think the trouble with these is it is very much a question of, if you now set them something to do, it would essentially be do this again. They're kind of the things that we're dealing with to do with these are kind of very clear-cut chunks of coding skills. And yeah, it does just come down to doing it and getting used to.
Yep. Well, if there's any more questions or any specific thing that somebody's lost on, just let me know. Otherwise, we'll move on to homework. But remember, at a very fundamental level, all we are doing is re-instantiating a dynamically instantiated array repeatedly so that it can fill more data. Oh, Florin, yes. He points out something from earlier. This code allocates 4 bytes on the heap, continuously requesting more and more 4 bytes, but it also allocates 4 bytes on the stack because of the val variable itself. Okay, so we're going to be talking about a linked list. I'll explain what a linked list is in a second, but the homework itself is going to be...
Right one.
Yep. The homework is that the homework itself is going to be write a linked list implementation using structures and functions. Allow the user to enter as many numbers as they want, allowing them to stop entering numbers when the user enters 0. Find the average of all numbers and display them to the user. And
yes, he does mean the mean average. Add all the numbers up and divide by the number of numbers.
Ungraded bonus, replace the vector used in last week's homework with your linked list. Again, that's an ungraded bonus for people wanting some more fun.
Sorry, have you looked at this thread at all since you posted it?
No.
Oh, that was why I got the sound of you looking blank. Although somebody did say that there should be bonus points for going ahead and calculating mean, median, and mode. But I think that's just silly.
Okay, doesn't software engineering cover linked list? It might. Linked lists are... Implementing a linked list is going to be one of the most important exercises you can do in regards to understanding dynamic memory allocation and pointers.
This is like Hello World for dynamic memory allocation.
Right. So with a linked list, the minimum requirement for a linked list is a single structure that contains, called node, that contains a few things. The first thing it contains is some data. And I know that might sound silly to put there, but I literally mean some data. Every node is going to be one value in your linked list. So in the case of the homework assignment, that value is going to be a single double value. Every node represents a single item of data within a linked list. The other thing that it must have, and this is for singly linked lists, is a node pointer to the next item.
Does that have to be called next?
It should be called next. So let's look at a vector real fast and how a vector looks like in memory. A vector in memory is always going to be a contiguous block. A contiguous block of items. You'll have I1, I2, I3, I4, I5, I6, I7, and I8. It's a contiguous block. That's what it looks like in memory. A linked list is different. A linked list is a bunch of nodes that may or may not be in any way closely related in memory. So you might have node 1.
I want you to put them all over the page.
And then you might have some additional memory right here. So just like more memory. It doesn't matter how much memory. And then you'll have node 2. And then a bunch of more memory. And then you might have node 3. And then a bunch of more memory. And you might have node 4. Every node contains a value. Whatever value you want each node to contain. In the case of the homework, it's going to be a double. But it also contains a pointer to the next item. that next item pointer is always going to point to the next item in the linked list.
Hence the name linked list. These are the links between the items.
Somebody actually asked a good question that I actually made a mental note to talk about, but hadn't. How can you create a node pointer within the node struct? Isn't that sort of like defining itself with itself? If it was a node next, not a node pointer next, you'd get a compiler error. Because you can't place a structure within a structure. You can't place a structure recursively inside of itself. Because that would result in chaos. The second you tried to instantiate it, it would just continuously, it would eat up an infinite amount of memory. However...
But remember, how big is next?
Yeah, how big is next?
Next is only... Yeah, who needs rhetoric? How big is next? All right, Moose, shut up. Yeah, next is a pointer. It's not a node. It's a pointer that happens to be marked as pointing to a node.
Right.
But it's a pointer, so it is just... that problem doesn't come up.
Yep. I do want to point out that all of the computers that I own are on 64-bit operating systems. The size of a pointer is not determined by the operating system you run it on. The size of the pointer is determined by the architecture your compiler compiles to. And because my Visual C++ compiler is compiling to a 32-bit process, that's why my pointers are 4 bytes. My operating system is 8 bytes, but your pointers aren't magically going to use more memory if you deploy it on a system that has a level of compatibility with a different architecture. I just wanted to point that out.
Yeah, I'm probably confused that issue by saying it a few times. Is that connected, just very briefly, with why x86 programs are supposed to go in that special folder for x86 programs?
Well, partially. I believe that's more of a convention that Microsoft put together, just to keep things separate.
Gotcha.
Okay. The goal of the homework is to implement this data structure. Given the definition of the data structure, it's going to be your job to convert this into code. And I've showed you everything you need to know to do that. If you have any more questions, please let me know. Especially if you have questions about what exactly the linked list is going to do or how it's going to work. Now, I highly encourage people, even if they don't immediately know how to implement this, to try. Because once you understand a linked list, I mean fully understand it, your concept of dynamic memory allocation and pointers will go up. I do want to at least point out the way that you add an item to the end of a list. Your linked list only needs to be a node pointer called first, typically. This is all your linked list needs to be. To add an item to the end of the linked list, you walk down the linked list until you find the last element, as in an element that's pointing to null as its next item. Then what you do is you instantiate a new node. And again, the memory isn't necessarily contiguous, so there could be a bunch of memory between these two things. But you instantiate a new node entirely, so node 5. You set its value to whatever data you want it to contain. You set its next pointer to null.
And here's the important bit.
And the important bit is you take the previous node and you set its next pointer to the address of the new node you just instantiated.
And I was going to say, if you could just write in down the left-hand side next to the N1, N2, and so forth, just write in some random memory addresses, please.
Yeah, like OX05, and then OX10, and then OXFE, and then OXFF, and I just ran out of memory. Whatever.
You can assume that you're missing out leaving zeros.
Yeah. So this might be OX253.
And now on the right-hand side,
right, the right-hand side.
You just show what the next value for each one is. for anyone who got it the first time will be sat there going, oh, yes, all right, yes, but just to make this ultra clear, because it does make this final example that little bit clearer. If you just show adding a node again.
Later, Musuru. Right, so if you add a node, so let's say we have an N6, and we instantiate it, and it gets instantiated to OX523. What we do is we set the value, we set the next pointer to null, and then instead of having this next pointer be null, we erase this and reassign the pointer to OX523.
And hopefully that should be crystal clear to everyone.
Yep. And even, I just want to make sure that people understand how a linked list works. Converting into code may still be a challenge, but please try hard, because this is like one of the best examples of both dynamic memory allocation and using pointers.
And just as a point of history as much as anything, it's one of the most clever ideas ever come up with. It's such a straightforward idea.
Yep.
That solves huge amounts of problems and just grafts.
Can you point back? You may, but that's a doubly linked list. What I'm looking for right here is a singly linked list.
Although, implementing a doubly linked list would actually be far less than twice the work.
Yeah, it would be pretty straightforward.
It would be it should be trivial, actually, given because it's the same knowledge required to do it.
Yeah, just.
And what is that normally called prev or?
Prev? Yeah, prev is typically what I do because I can't spell previous.
Prevoice. But, well, cool. That seemed relatively painless. Yeah, deadline is on the thing, on the homework page. I can't remember what deadline you set for it. But you have got an extra week to do this.
I think I set the deadline to May 25th, next Friday.
I think so. Friday, yeah. And also on that subject, because obviously next week we haven't got any classes.
Yeah, next week.
So
we're going to be doing.
Yeah. So we are going to be doing 2 open office hours for coding. We were going to be doing one on Monday at the same time as the C++ class would be, so that's probably not going to be of much interest to you. Did we decide when we were doing
either Friday?
Whether we're going to do Thursday or Friday?
Probably Friday.
Probably Friday. In this session we are going to be doing another open office hours, but it may be Thursday at this time, which is the C# session time.
Well, I think the C#. The C# people are going to be welcome to attend either.
Everyone, yeah, I would say everyone's welcome to attend either. But it just happens that we decided to take the opportunity of having one session at either time, because obviously people with only the one open office hours, people are struggling to make it who live in certain parts of the world. And yeah, dual op amp, very much so, in fact, like pathfinding. Yeah, is there anything else we need to...
No, I think I'm about to hit the stop button on the recording. So,
well,
yeah.
Excellent. Now you all know everything about pointers.
Yep. Goodbye, everyone.